In this video, we're going to implement a pseudo-spectral solver for the Navier-Stokes equation, which simulates the Taylor-Green Vortex. It will be a translation from the Spectral DNS in Python paper by Mortensen and Langtangen. Let's get started. Hi and welcome to this new video. We're going to implement an incompressible Navier-Stokes solver that uses a pseudo-spectral approach. That means we will be both working in Fourier Domain and in Spatial Domain, and we will switching between the two using the Fast Fourier Transformation. As mentioned in the intro, this will be a translation from a Python code from a paper that is called Spectral DNS in Python. I can highly recommend this paper if you want to dive into more detail on the method we're going to use. I've listed the Navier-Stokes equation, or the incompressible Navier-Stokes equation, here again. However, we will solve them in a reformulated way that takes advantage of the Fast Fourier transformation. But before we go over the solution strategy, I first want to look at a scenario. As you've seen in the intro, this will be a three-dimensional simulation. And for this, we will look at the so-called Taylor-Green Vortex. This Taylor-Green Vortex takes a cube domain, which goes from 0 to 2 pi in each of its three axes. And in each position in this three-dimensional space, we will initialize our three-dimensional velocity field according to this here. So the u velocity will be initialized, the v velocity, and the w velocity will be set to 0 throughout the domain. Then there will be no forcing, in other words. And this initial vortex that is within our domain then slowly transitions into turbulence and kind of experiences multiple stages. There's a really cool analysis. I also put the link in here. So what we will be seeing is first so-called laminar vortex sheets, and then a process that is called vortex stretching, something that can only happen in 3 dimensions. That's also the reason why sometimes when you see Taylor-Green Vortex simulations in 2D, those are not turbulent. Those actually also have an analytic solution. The step after vortex stretching is some rearrangements. More interesting though is breakdown and the fully turbulent stage. And towards the end of our simulation, we will then see dissipation and decay, and all the small grain structure of turbulence will be lost. Interestingly, one can perform an analysis once these particular stages occur. However, here we will just look at them a little bit more loosely. Okay, how does this pseudo-spectral solver work? This is going to be a little bit more difficult, but later on when we implement it, don't worry, we will go over the stages in much detail, and probably seeing it alongside the code will help you understand it even further. So for this, I first want to introduce some notation. Since we will be both working in Spatial and Fourier Domain, I decided to give the variables in both domains special names. So of course we have the velocity field u in Spatial Domain, and then I called it lambda in Fourier Domain. So once we apply the Fast Fourier transformation on u, we get lambda. If we apply the inverse Fast Fourier transformation on lambda, we get u. Then we have omega. Omega is the vorticity field. So essentially, this is when we apply the curl to it. So this is nabla cross product u. And we both have it in Spatial Domain as well as in Fourier Domain. Also be aware that u, lambda, omega, and eta are 3-dimensional vectors. Then we will have an intermediary product, I just called m here. This will be the product of vorticity and velocity. And here we have it in Spatial, and there's an error. This should be Fourier Domain. Then we have the wave number. This is essentially the wave number our FFT is computing the coefficients for. And this one is also a 3-dimensional vector. Then we have psi. This will be the pressure, or more precisely a pseudo-pressure in Fourier Domain. This one is a 1-dimensional scalar. 3-dimensional vector means that at each point in our 3-dimensional domain, we have a 3-dimensional vector. And 1D scalar means that at each point in our 3-dimensional domain, we have a 1D scalar. Then we have B, which will be the right-hand side of our ODE system in Fourier Domain. Again, also a 3D vector. And then we have I, which will be the imaginary unit. It's a 1D scalar. Okay, our algorithm starts with first an initialization. We will initialize the velocity tensors according to the initial condition. So this is what we had here with uv and w. And then we transform them into Fourier Domain. Okay, then first step, we will compute the curl in Fourier Domain. And the curl, as it is displayed here, is nabla cross product u. And if we transform this operation into Fourier domain, then we will get this is equal to imaginary unit times wave number cross product velocity in Fourier domain. You know, we have this velocity in Fourier domain from the initialization or from the previous iteration in the loop. This k is given, it is constant throughout the simulation, and I is just the imaginary unit. So in essence, we now get our eta. Then we can transform the vorticity back into spatial domain with an inverse fast Fourier transformation. Then we compute this m, which can be thought of as a convection somehow. So we will do another cross product between u and omega. So this u is either from the previous iteration or from the initialization. This convection can then be transformed back into Fourier domain. So you see we're going back and forth. And essentially the reason we're doing this is that certain operations are better to be done in Fourier domain and some others are better done in spatial domain. And since the fast Fourier transformation is such an efficient operation, also with a really efficient implementation, we can run reasonably large computational domains in an acceptable time, which is just amazing. So then we are in Fourier domain. So this is the phi vector here. Then we need something that is called a Dealiasing. And you can think of it as if you've played video games and you have anti-aliasing, if you have a staring effect on certain edges, this will essentially allow us to remove certain high frequency elements. And the reason we have to do that is that just because of the resolution we're going to use, there are certain wave numbers we can't resolve. And by not resolving, we mean we don't compute for. So we should kind of smooth our solution a little bit in order to be stable. Then the sixth step is to compute the pressure, or maybe you could also call it the pseudo-pressure in Fourier domain. And this pseudo-pressure is usually obtained, or in spatial domain it's obtained by solving an elliptic problem or an elliptic PDE. And interestingly, this elliptic PDE can be solved directly in Fourier domain just by a dot product. So we kind of have a dot product here because remember, k is a 3D vector, phi is a 3D vector, and psi will be a scalar. And the psi can then be used in order to assemble the right-hand side to the ODE system. And here you see a lot of contributions. You have the contributions from the convection, and then we have a contribution from a diffusion, and then we have a contribution from a pressure gradient. And pressure gradient, again, differentiation is really easily done in Fourier domain. So here we also don't have to use proper differentiation, but rather we will use multiplications with the wave numbers. And then essentially this B defines the right-hand side to an ODE system. And then we will just use an explicit Euler time step in order to advance our solution in Fourier domain. And again, recall lambda was the velocity field in Fourier domain, and this one has then to be transformed back into spatial domain, so in U, and this can then be used in the next iteration again. Then the 10th step is optional, but we will do it here because it is just visually pleasing. We will visualize the vorticity magnitude in spatial domain. And you know we have that available because we did this in step number 2, where we transformed the vorticity back to spatial domain. And then we will do an interactive isocontour plot using Makie.jl, which also runs in real time. It's just mind-blowing to me. And this is also what you've seen in the intro. And then we will repeat the process over and over again. And this is our transient simulation. And just as a conclusion, that in total, it takes us three-dimensional Fourier transformation. So we have that once here, where we do an inverse transform, then we do a forward transform, and then we do an inverse transform again. And inverse and forward transform, they are of identical complexity. So in each temporal iteration, we do three-dimensional Fourier transforms. And again, it's called pseudo-spectral because some operations are in Fourier domain and others are in spatial domain. And then there is one thing I want to make you aware of that we have to consider for stability. So don't choose the time step size too large. So this kind of has to be chosen in accordance to the rest of the parameters. You can select. And then of course, take a look at the Python repo. So this is not a direct translation, but it is heavily inspired by this spectral DNS paper. And there's also a short version of it, which uses Python and MPI if you rather want to have it in that particular language. And with this, we can finally get started. Okay, let's have the imports first. And we're going to be using FFTW for our fast Fourier transformation. Let me just move that up real quick. Then we will use GL Makie, which is the OpenGL interface to Makie. Makie is an advanced plotting library for Julia, which also allows for really fast three-dimensional plots, which is just amazing. And so we don't have to write it out and then visualize it in another software like ParaView. Then we will also use statistics for some shortcuts. And I want to use the progress meter package in order to, display the progress. Then let's define some constants. So first we need the number of points per axis. So we will use a uniform Cartesian grid. So the number of points per axis is identical. This is just defining the computational load or simulation. For me, I figured out 50 is a good solution. Usually values that are exponentials of 2, so 2, 4, 8, 16 and so on, tend to work faster because of the properties of the FFT. But you also have to keep in mind that the visualization also becomes harder the more points you have, especially if you want to do it interactively. Of course, if you have a beefy machine, go higher, or if you don't want to run interactively, you can also go to higher resolutions. Then let's define the kinematic viscosity. This indirectly also defines the Reynolds number. So here I want to have 1 divided by 1600. Then let's have a time step length of 0.02. And I want to perform 1700 time steps. So maybe let me use that syntax. And then I want to plot every third time step. That kind of gave a really interesting and nice to look at plot. Okay, then let's create our main function. So function main, leave it empty for a second, then with an end command and just call it such that we have our main function done. And then the first part is to create our mesh and the wave numbers. So for this, we first discretize in each of the 3 coordinate axes independently. So we have some sort of an X range. For this, we will use Julia's range command in order to distribute from 0 to 2 times pi endpoint per axis points. So this will just equally space endpoints per axis between 0 and 2 times pi. Something similar can be done for the Y range. I will just copy that, and for the Z range. And then we have to mesh these 3 into big tensors of our coordinates. This is just helpful for some convenience later on. This is equivalent to using the mesh grid command in NumPy or MATLAB. For this, we will first have coordinates in X, which will be a 3-dimensional tensor that contains all the X coordinates of all the points in our mesh. And for this, we will use a nested list comprehension. So opening, closing brackets, and then say X for X in X range, Y in Y range, and Z in Z range. And basically the same is done for coordinates Y, except for no using Y for X and X range and so on and so forth. And Z is identical. So an coordinate is of course a 3-dimensional vector, and then we have a coordinate for each of the point in the mesh. So this is basically this collection of those. Then we have to do something similar for the wave numbers. You can think of a wave number as whatever you see in front of an X inside a sine function. And this is just related to the number of points that we have. There's a convenient shortcut in FFTW in order to create these frequencies. And for this, I want to do wave numbers 1D in X, which is going to be given as FFT frequency of n points per axis. These FFT frequencies, though, are scaled by 1 over n points per axis. And in order to revert that scaling, we element-wise multiply with n points per axis. Let's copy that, and we have something similar in y direction and something similar again in z direction. And then we can basically mesh them up similar to our ranging, because of course here in 3 dimensions we also have a 3-dimensional wave number associated with each point in the 3-dimensional Fourier domain. So we have a wave numbers in X, so wave numbers X is going to be again nested list comprehension, and here we will do kx for kx in wave numbers 1dx, ky in wave numbers 1dy, and kz in wave numbers 1dz, and just copy that twice. Then we have the wave numbers in y with ky and the wave numbers in z with kz. And then we also need the wave numbers norm. So as said, the wave numbers are also a 3-dimensional vector, and we can take the norm of this 3-dimensional vector. So in our particular case, we just do wave numbers norm is going to be the element-wise square root of wave numbers in x, element-wise raised to the power of 2, plus wave numbers in y, element-wise raised to the power of 2, plus wave numbers in z, and again element-wise raised to the power of 2. And then if we look at the steps in our algorithm, we see that at certain points we could also use so-called normalized wave numbers, which is just the wave number divided by its norm. So here we have it, and here we also see that. And that's kind of reasonable to pre-compute, so let's do that. We do an normalized wave number, so normalized wave numbers in x is going to be the wave numbers in x element-wise divided by the wave numbers norm. Same strategy in y and z, so y and z here and y and z there. Now we just have to account for one particular thing, that one wave number is going to be 0, so it will have a 0 norm. And dividing by 0, of course, it's always a little troublesome. And a quick fix is just to set the wave number at that particular precision to 1, such that we divide by 1, and then there should be no issues. So we do wave numbers norm exist at is 0, element-wise applied to the wave numbers norm, in order to indicate where the 0 spot is, and then we set this point equal to 1. And since we no longer need the wave numbers norm array afterwards, it's also fine to modify it here. Then let's translate our initial condition. So the Taylor-Green Vortex initial condition. And so we will have a velocity in x, which is going to be the sign element-wise applied to the coordinates in x, then element-wise multiplied with the cosine element-wise applied to coordinates in y, element-wise multiplied with the cosine of the coordinates in z. Then the velocity in y is going to be a negative cosine element-wise on coordinates x, element-wise multiplied, and here we have the sign of coordinates y. So this is literally just a translation of what we had in the intro doc string, and another cosine here. And then our velocity in z is going to be a zeros-like tensor, so we will do zeros, and it will have the same shape as the other velocity arrays. So we will just do endpoints per axis, and we need to put that into a tuple. So endpoints per axis, endpoints per axis, endpoints per axis. And here this again highlights that each of the velocity tensor is a 3-dimensional tensor to represent the individual component inside of this 3-dimensional mesh. And then we will do an pre-planning of our fast Fourier transformation. This could potentially yield a computational performance increase. So this is pre-plan the FFT for additional performance. For this, I want to create a FFT operator, and this one will be plan FFT applied to velocity x, and then I want to use the flex called FFTW.measure, which performs some quick measurements on our array in order to determine optimal parameters to perform the FFT, hopefully even faster. Problem though is with this particular flag that our array is potentially overwritten, so we will just rewrite it again. So I'll copy that down and use it here. And then we just have to pre-allocate some arrays such that they're not allocated over and over during our time loop. And so what we're going to need is first our velocity x FFT. And if we look at the algorithm, we see step 0 was not just initialize the velocity vectors, but also transforming them into Fourier domain. So this is also some sort of a pre-allocation. So pre-allocate arrays. And we can apply our Fourier operator by just saying FFT operator multiplied with the velocity in x. And then this is just a copy and paste task. So velocity y, velocity z. And here we have velocity y and velocity z. So then let's predefine our curl array. So we have the curl x, which is going to be zeros. And the data type of the zeros is going to be float 64, and then it will be of shape n points per axis, n points per axis, n points per axis, and then we can just copy that down and create a curl y and a curl z. This is a little tedious for our visualization later on. I also want the curl squared in order to compute the magnitude. So this will be curl y squared, curl y squared. You see, this is getting a little tiring. And that's our curl squared. Then we of course also need our curl in FFT. So I will copy this one down. And in Fourier domain, of course, our data type will be a complex version, so complex of float 64. And then we can just copy that again and have curl y and curl z. And of course, here we need the suffix FFT in order to denote that this is the curl in the Fourier transformation or the Fourier domain. And then we also have our convection arrays. So I will also copy that down. You see, this is really getting tiring. So this is convection in X and convection Y, convection Z. So Y and Z. And the same thing has to be done in our Fourier domain. So convection X FFT. And this one again will be a complex data type. And just copy paste. Feel free to skip ahead if this is a little boring to watch. And the last one is our curl magnitude. So I will just take one of the curls here and put it right below and say this is the curl magnitude. That's the one we're going to visualize later on. And then we also need to pre-compute some stabilization. So this was the De-Aliasing I mentioned earlier, such that we can't resolve higher wave numbers. So I will call this De-Aliasing is necessary to stabilize the simulation. And for this, we have to first figure out the maximum possible wave number that we resolve. So we can approximately only resolve 2/3 of the wave numbers. And since we have positive and negative wave numbers, we go about 1/3 into the positive direction and 1/3 in the negative direction. And everything that is above or below that will be aliased away, you could say. So Kmax De-Alias is going to be 2/3, so this is a 2/3, multiplied with n points per axis, integer division by 2 plus 1. So in essence, if you maybe make the simplification 2 by 2 cancels out, we have approximately 1/3 of the points. And then we want to check whether the absolute of our wave number is larger than that. And in that particular case, we want to, basically get an 0 and below that a 1. You will see that. So then we have a De-Alias. So De-Alias is going to be, first we check the absolute of the wave number in X is going to be element-wise smaller than Kmax De-Alias. And here this means, of course, that we check whether the absolute, so this means independent of whether it's positive or negative, is smaller than that. And if that is the case, the alias shall be true, and true refers to a 1. And otherwise it's a false, will be 0. And later on we will element-wise multiply this De-Aliasing tensor with our current coefficients that we got from the FFT. And by doing so, we just kick out all the high frequency elements. And then we will have element-wise multiplication. You can also think of it as an element-wise AND operation for these booleans. And then I will just copy that down twice actually, and let me change the wave numbers y and wave numbers z. And it seems like I did a small mistake here, so we have to remove this additional set of brackets here. Okay, then we're good to go, and we can finally start with our time loop. So let's do an add show progress and say simulating and animating or visualizing, and then we will do for t in 1 to n, not n points in time, but n time steps, and then an end. Okay, then step number 1 in our algorithm, let's check. This was compute the curl in Fourier domain, and computing a curl is a differentiation operation in spatial domain, but luckily due to the Fourier domain we only have to do a multiplication with the wave number and with the imaginary unit. And for this I want to implement a function which performs the cross product on our three-dimensional tensors. And this is helpful because we will use it at another point later on. So let me go right above the main function and implement a function called cross product. And this shall be a function that operates in place. So we will add the exclamation mark. And this function shall write its results into a result X array, a result Y array, and a result Z array. And it should take an AX array, an AY array, an AZ array, and a BX, a BY, and a BZ. So basically it takes two vectors, so a vector which consists of x, y, and z, and a b vector consisting of x, y, and z, and write the result of our cross product into this here. And then let's have an end here. And I just want to highlight the types that we accept here. So these shall be arrays that are of type T and three-dimensional. So they have 3 axes. And all of them should be like this. So let me just quickly do that for all. So these are arrays of a type T with 3 axes. And these 3 axes are of course because we simulate a three-dimensional domain, which we have discretized using a uniform Cartesian grid. And here we go, almost done. So these are our arrays. Okay, last one, here we go. And the reason I'm using T here, because I want this to be a templated function, because I want to say where T is a subtype of the union between float for 64 and a complex of a float 64. And this will basically allow us to call this function on both arrays in the spatial domain as well as in the Fourier domain. And then we will just apply a cross product. So this is basically where you always forget how it works. So I hope I'm doing this correctly on the first try here. So we will have the result X is going to be given, and we will use the dot equal in order to directly write into the array in order to have this in-place operation to avoid allocations in our time loop. And this one will be given as AY element-wise multiplied with BZ, and then element-wise subtracted by AZ element-wise multiplied by BY. And then we get our result in Y by using the dot equal syntax again. And then here we have an AZ element-wise multiplied with a BX, and then element-wise subtracted with an AX element-wise multiplied with a BZ. And then lastly, we have our result in Z direction, and here we have dot equal again. And then we will use an AX element-wise multiplied with a BY, and then subtracted, not multiplied, sorry, subtracted. And here we will have an AY element-wise multiplied with a BX. Okay, here we go. So then we can remove this last line here. And this is now basically a function that we can handily use in order to compute the cross product whenever we need it. So let's go down to our time loop again. And then we compute the curl. And for this, we will call the cross product function, so cross product. And I want to save the result in curl FFT, so curl X FFT, curl Y FFT, curl Z FFT. And then we want to do the cross product. Let's look at our solution algorithm by doing IK cross product lambda. So this is the velocity in Fourier domain, and this is going to be our wave number, and that's the imaginary unit. So let's first have an A vector. This is going to be IK. So let's go down, and this one is imaginary unit element-wise multiplied with wave numbers in X, and then IM with wave numbers in Y, and IM with wave numbers in Z direction. And then our B is going to be the velocity X FFT, velocity Y FFT, and velocity Z FFT. And of course, this velocity X FFT is available from the previous iteration in time, and for the 0th time iteration, we have it from the initial condition. Step number 2 was to transform the curl back into spatial domain. Transform curl to spatial domain. I mean, you can't say transform back because we computed it in Fourier domain. Either way, we now have that the curl in X is going to be assigned to the FFT operator backward slash on the curl X FFT. And what this does is it applies the inverse Fourier transformation, so we can use our Fourier operator in both forward and inverse direction. Although we have to be careful, since we're not using a real Fourier transformation and a general complex Fourier transformation, this can, due to numerical rounding issues, yield a complex result. And of course, in spatial domain, we only have real values here for our simulation. So let's call the function real on it, which just extracts the real part of an imaginary, or sorry, a complex number. And we can do the same for the curl Y and Z. So curl Y, curl Z. And here we have curl Y, curl Z. Okay, this is step number 2. Let's go on to step number 3, which is to compute this convection term. I will put it in quotation mark in spatial domain. And for this, we will again use a cross product, but here it is, not a differentiation, but just a proper cross product. And so we will have cross product of, well, we will save the result in the convection arrays. So convection X, convection Y, convection Z. And we will use the velocity and the curl array. So we will use velocity X, velocity Y, and velocity Z, and then we have the curl array, so curl X, curl Y, curl Z. And here again we have the velocity from the previous iteration, and in the 0th iteration we have it from the initial condition, and the curl we just got from the cross product we did in Fourier domain. And now we have some sort of a convection array here. This has to be transformed back into Fourier domain, so this is step number 4. So to transform the convection back to Fourier domain, well, maybe back is not the right word, let's remove that. I mean, it has never seen the Fourier domain before. And then we basically get a convection X FFT, which is going to be dot equal the FFT operator multiplied or applied to the convection in X. And let's just copy that down, convection Y FFT, convection Z FFT. You see, we have these kind of repeating lines with just a little bit changed in them. Then we have our de-aliasing step. So step number 5, which is de-aliasing. Sorry, I always get this wrong. De-aliasing on the higher wave numbers. And for this, remember we created this de-aliasing tensor that we have here. And this de-aliasing tensor is a Boolean tensor, but you can also think of it as an integer tensor, where that it is 1 at certain frequencies or wave numbers, and it is 0 at others. And it is in particular 0 at those wave numbers that we cannot properly resolve. So we will multiply that with this convection term, and by doing so, we ensure that we don't compute wave numbers that we can't resolve. Okay, so we say convection X FFT is going to be point multiplied equal the de-aliasing. So element-wise, multiply with de-alias and save it back in the same array. And let's just copy that down and do it for convection y and convection z as well. Okay, now we have the convection step done, and we now have to compute our pseudo-pressure. Let's look at the algorithm for this. So here we are now doing step number 6, and we have to compute this psi here. And for this, we will do a dot product between the normalized wave number, so because we can first normalize it, and then with pi, which is the convection that we just de-aliased. Okay, let's get down and do that. So we will have step number 6, which is to compute the pseudo-pressure by a divergence in Fourier domain. And then we will have a pressure FFT, which is going to be the normalized wave numbers that we created element-wise multiplied with the convection XFFT, and then plus the normalized wave numbers in Y with the convection YFFT, and you get the pattern, plus normalized wave numbers in Z, element-wise multiplied with the convection ZFFT. Well, and then we are essentially left with the assembly of the right-hand side to our ODE system. So let's do that. This is step number 7, to assemble the right-hand side to the ODE system in Fourier domain. So we will have the right-hand side XFFT, which is going to be the convection XFFT minus the kinematic viscosity multiplied with the wave numbers norm squared, element-wise multiplied with the velocity XFFT. So this, as said, is our diffusion basically. And then we subtract the normalized wave numbers in X, element-wise multiplied with the pressure FFT. And this will be our pressure gradient contribution. So I will try to copy and paste and hopefully not make a mistake by doing so. So right-hand side YFFT, let me scroll down a bit, is going to be convection YFFT. And then here we will have the velocity YFFT, and we have the normalized wave numbers in Y direction. Okay, of course this should be Z, so maybe let's change that to Z. So velocity ZFFT and Z here. Okay, here we go. Hopefully that's working now. And then finally step number 8. So step number 8 is it, which is the Euler step update. And we will just say velocity XFFT is point plus equal the right-hand side in XFFT multiplied with the time step length. So just an explicit Euler update. And again, copy paste for Y and Z direction. So Y and Z. And here we also need Y and Z. And then lastly, of course, we now have updated our velocity in Fourier domain. But for the next iteration, we again need it in the spatial domain. So we will transform it into, in its original form, basically. So step number 9 is going to be to transform the original velocities back to spatial domain, or maybe let's call it the original, but the velocities. Then we will have velocity x is going to be point equal the real part of the FFT operator inversely applied to the velocity x FFT. And again, I copy and paste the action with Y and Z. Probably one could have also done this a little bit more elegantly. And here it is now, though. And this is also the update in the time. So if we go to the, where is it, our algorithm again? So this is the repetition part. Since we've now overwritten U and UFFT, we can basically start with a new iteration by, again, first computing the curl and so on and so forth. Okay, lastly, let's look at the visualization step. So let me go all the way down here and say, now we're doing the visualization. Well, why not use capital letters here? And for this, I want to first check whether we are in an iteration where we actually want to visualize in. So if t modulo the plot every is 0, then I want to visualize. And what is it that I want to visualize? So as said, we want to see isocontours of our curl magnitude. For this, we first have to compute the curl magnitude, and we can do that by computing the norm of it. For this, I want to first get the curl x squared, which is point equal the curl x element-wise squared. And the same, I mean, now you've seen it a couple of times in y and z direction, y and z. And then we can use these squared components in order to get our magnitude. So the curl magnitude is going to be point equal the square root element-wise applied to curl x squared plus curl y squared plus curl z squared. And now we have a three-dimensional tensor containing a scalar value, so this is the magnitude, and this allows us to draw three-dimensional isocontours. And this is what I want to do with Makie. So in order to get Makie started, I mean, we will do it a little bit hackily because we want to interactively update the plot. So I figured out some hacky way of doing that. Might not be the best way. Feel free to leave a comment if you think there is a better way and probably also a more efficient way. Either way, let's try that. For this, let's go all the way up in front of the time loop in order to prepare the visualization. So I want to call this prepare the visualization. And for this, we first create a Makie plot window. So we will say Makie plot figure window. It's going to be figure. So this will instantiate a Makie figure. And then we also want to display it. So I will say display Makie plot figure window. This will bring it up. And then inside this figure, we can create an axis. So I want to call this Makie plot axis. And this one is an axis 3 for a three-dimensional axis. And so we will say Makie plot figure window. And then I will index that at 1, 1. I haven't fully understood Makie yet. I'm on the verge of learning it, but I would interpret it in the way that we could use subplots here, but we only want to have one subplot in our plotting window. And since it is a three-dimensional plot, we need some sort of a projection from three-dimensional space to, well, the two-dimensional space our monitor is made of. And this can be adjusted by the perspectiveness. And here I just want to use 0.3. That's kind of, I think, a decent compromise between the two ways of doing 3D projections. And then I first want to plot something in there, probably something stupid, but the reason I want to do that is that our plot kind of is prepared and everything is loaded up and all the things that potentially need compilations are compiled. And so I will create a Makie plot 3D contour, which is going to be a contour exclamation mark in order to tell Makie to plot into a particular axis. And we want to be plotting him into Makie plot axis with the mesh given by X range, Y range, and Z range. And then it shall be plotting the curl magnitude. I mean, you could potentially use any other three-dimensional tensor here that matches the correct shapes. And I want it to have an alpha value of 0.05. Let me add the spaces here. And I want to plot it over levels. So these are basically the values, the scalar values at which we want to see isocontours. And here I want to have them between 0.2 and 1 with a length of 4. And now I just want to basically wait till Makie created the plot. So it will somehow do that in the background. So I will just print out, say, hit enter when plot is ready. And then I will just do a read line. And so basically we will just wait for a couple of seconds before that's ready. I mean, it's just a hacky way of doing that, but you will see why we need that in a second. Okay, this was the preparation. Now we can go to the actual time loop. And here I first want to delete whatever is inside the plot. So I will do a delete. And in order to do that, we have to somehow access the parent. As said, it's a little hacky. So we will do Makie plot 3D contour dot parent and then Makie 3D plot contour. And the dot parent is basically the 3D scene in which we created the contour plot. And this tells Makie to delete the previous contour plot and which was in this scene. Either way, let's try to create the new contour because we want to override it in each iteration where we visualize. So we do a Makie plot 3D contour is equal to a contour exclamation mark again. And basically I can just copy what I had up here. So I will just copy that, go all the way down and paste it in, and then maybe just 2 more indentation levels. And I see here I used other values, so this shall be 0.01 for the alpha value, and this one should be going from, maybe let's do this new entirely here, and this one shall be from 1.0 to 10.0 with 5 entries. So it's basically just a little bit of an engineering, seeing what kind of curl magnitudes appear over the course of the simulation, and then choose a subset of ISO values that might be pleasing or like interesting to look at. And just to give Makie enough time in order to update everything, I will just let the Julia code sleep for 0.02 seconds. Well, and that's already it, our implementation. Let's give it a try and see whether we have any errors. Probably we have. So let me execute that. And I already see that there is this issue with my VS Code that it has imported something I didn't want it to import. So I now can execute Julia Taylor-Green Turbulence. Let's see. And we have quite a long startup time since these initial compilations for Makie will take some time. Okay, here we go. Now it created the plot. I mean, so far we haven't seen any errors, but they could still be inside of our code. So what you see here is basically marking, caching some fonts and preparing all the stuff, pre-compiling. So as you see, the Julia code would already be ready and would start computing, but Makie wouldn't be ready in visualizing the results. Okay, finally, here we are. So we see our 3D scene, and we can actually also, move it around if we wanted to. So I will just move that into the foreground, and then it says hit enter when plot is ready. I mean, the plot is ready, so I hit enter, and then our simulation starts. Hopefully, let's see. Yes, amazing. So we see the ISO contours, and we also now have to be a little bit fast and commenting. So we see kind of first these laminar vortex sheets, and then we have vortex stretching, and here it's already breaking up into turbulence. So that's also why we see kind of a clouded mess of nothingness. But in essence, this is just some super tiny small grain structures. And be aware that here we're using a resolution which is actually not sufficient for turbulence simulations at the particular Reynolds numbers. So if you have a more beefy machine, you should probably go to maybe something about 250 or higher. Anyways, we will still see some turbulence, although it's not that interesting to look at. We see that with the opacity. And now, as you see, it's getting a little bit more lighter because it's kind of dissipating over time. But we will see kind of a comeback for a little bit. So give it some time, and I think now it's having its comeback a little bit, so it's getting denser, so we see stronger vorticities. But overall, you see the structures are agglomerating into larger ones. And now we should be approaching the dissipation. So now it's getting lighter, and you see the distances between the vortex structures are getting smaller, and we're almost towards the end. It's almost done, so it's really a little bit of nothingness here. And there we go, that's a simulation. Okay, I'm quite surprised that there aren't any errors here. If they were, then I will of course probably highlight them within the code and also leave a comment afterwards. If you spotted any mistake, this could definitely be the case. And also with respect to the mathematics, I would be super happy to hear your thought down in the comment section. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. This is now the end of the video. If you enjoyed these kind of videos, like super simple implementations of various simulations, let it be in Julia, let it be in Python, then subscribe to the channel. There is more like this on the channel, and there will also be more like this in the future. And hit the thumbs up if you enjoyed it. Leave a comment if something is unclear, or if you enjoyed it, share it with someone you think that might be interested in that. Here you will now see similar videos, and I hope to see you in one of the next videos.